Thank you everybody for coming. My name is Bryan Helmkamp. I'm really excited to be here in Philly. This is my first time at Philly ETE, and I'm also very excited to be presenting to you today. Philadelphia seems like an awesome city every time I visit it. I love it. A lot of culture, history, great beer. That's one thing I've noticed. And I've really been enjoying some exquisite culinary experiences also. I was happy to learn that if I eat only cheesesteaks, I only need to eat once every 3 days. That's actual size at Ishkabibbles. I started a company called Code Climate about 5 years ago. Who's heard of Code Climate? All right, the rest of you will have to chat after this. Come see me up here. But we do automated code review using static analysis. And so every day we analyze over 75,000 repositories, try to identify things like defects, maintainability issues, cases where people are writing code that for whatever reason has some sort of problem that they might be running into. We help about 60,000 developers through the course of doing that across over 1,500 organizations. So every day we live and breathe the idea of code quality and working with developers to help them improve their code quality. And that's what I want to talk about today a bit. So we're going to look at 6 questions. The idea with these 6 questions are just insights or sort of things that were a little bit surprising to me that I've learned over the course of my time at Code Climate, and hopefully it'll inspire some interesting thoughts for all of you, and maybe we can discuss these things a bit at the end of the session. So if you have ideas for questions, we're going to be running a mic for questions, but please feel free to jot down a note and we can talk about them at the end. So the first question is an obvious one. What is code quality? Code quality seems like a very touchy-feely concept, like it might be a little bit hard to define. So one thing that I think might be easier to start with would be looking at something that's sometimes considered the opposite of code quality, which would be legacy code. Maybe if we can define the opposite, then it'll be more clear what code quality is. So legacy code, everybody knows the definition of legacy code. It's a noun. It refers to code written by somebody else or code written by me more than 2 weeks ago. All of that is legacy code. So quality code is not legacy code. But in reality, code quality has many meanings. If you ask a developer, and we do this regularly, what does it mean to you to be writing quality code or for your team to be producing quality code, you'll hear a lot of different adjectives. You'll hear things like the code should be simple, the code should be well tested, bug-free, clear and understandable, it should have meaningful names that are coherent to the people who need to read it. Refactored, right? So someone's gone in and optimized the code to sort of suit their understanding of it. Documentation can be, in some cases, a controversial aspect of code quality. Some teams try not to use inline code documentation. For other teams, it's a pillar of their code quality regimen. Extensible, also sometimes controversial. How easy is it to build on this code? Versus how important is it that it is extensible before it needs to be extended is something you hear a lot of talk about. And fast, arguments, depending on the type of system that you're implementing, the performance of the code at runtime could be considered a key aspect of its code quality. So in hearing all of this over these years from different organizations and different developers, these different definitions of code quality, what I've really come to feel is that the first thing you need to do to improve code quality within your organization is to make sure that everyone on your team is on the same page about your goals. And many times if a team fails to adopt a tool like Code Climate to help them improve their code quality, you can trace that back to there being disagreement about what they were even trying to achieve in the first place. So a simple example of that might be around the structuring of code or organizing your code into things like modules and classes. What we've seen is that every team tends to have different stylistic preferences for how they organize their code. And as a result, you see teams with different styles and different sort of average class sizes, that sort of thing. So I came across this quote, which I really like. Any code less decomposed than mine is a mess. Any code more decomposed than mine is over-engineered. And this is universal truth, and everybody can feel that. So I don't have an attribution for this. If someone finds it, let me know. But this is why you need to make sure you have a shared definition of where you're trying to go up front. Otherwise, you could have a situation where you're doing a lot of work and not really generating impact in terms of the way that work is being perceived by your developers. That's the first lesson. Number 2 is what's the best way to measure the complexity of code. There are a lot of different ways to measure code, which we're very familiar with. There's sort of the most important metric, which you can use getting code reviews, which is WTFs per minute. You can see in the cartoon, the code review that's on the left side is going quite well, whereas the code review on the right side is a bit more colorful, indicative of the lower quality of the code. But there are a lot of different metrics that you can look at with things like static analysis. So static analysis just means information you can derive from a code base by analyzing it with other code. And you might have heard of metrics like cyclomatic complexity. Sometimes that gets referred to as McCabe's complexity. And it refers to the number of linear paths through a given unit of code, like a method, for example. Another metric, a little bit less known, is the ABC metric. So in this, ABC stands for assignments, branches, and conditionals. And so the ABC metric is a way to take the number of assignments, branches, and conditionals in a unit of code and aggregate it into a single score for that piece of code. And generally, code that is more complex will have perceived to be more complex will have a higher score, so it can be directionally accurate. My favorite static analysis metric, after doing it for 5 years, is very clear. It's lines of code. It correlates incredibly well with how difficult the code will be to maintain. The more of it you have, the harder it's going to be to maintain, almost certainly. And actually, if you were to take the same pieces of code and compute the cyclomatic complexity, the ABC scores, and count up the lines of code, you will see, perhaps not unexpectedly, an incredibly tight correlation between those metrics. So this is the actual algorithm for ABC complexity. You square each of the component parts, sum them together, and then take the square root of the entire value. Now, when CodeClimate started, we only had a few different checks that we would run against a code base, and 2 of the 3 of them were what we called complexity checks. So we would analyze the complexity of a class or a method, and then look at the score, and we use this ABC metric to compute that. One of the reasons that we did that was there was an open source library available for Ruby that made that that was somewhat popular and made that pretty easy to do. So we said, well, why don't we just start there? We can just pick a number and say, well, if your ABC metric for a given class is above X, or your ABC score for a given method is above Y, then we will report it as being too complex. Simple enough. And that's how CodeClimate worked for years and years. And actually, that's still how a number of our customers are still using it. But when we would talk to developers about this type of metric, we would start to hear the same things over and over again. So one thing we would hear is they didn't know where the number came from. So we would tell them your class has a complexity of 63.5. And of course, a developer, the first question they're going to ask is, well, how did you compute that? Right? So if you can't drill down into the metric, developers don't get a whole lot of value out of it. The next thing that they would say is, well, that's great, it's 63.5, but what do I do about that? Right? I don't know how to improve the ABC value of a piece of code in the abstract. I just know how to do things like refactor and extract methods and those sorts of things. But it's not exactly clear which of those refactorings are going to have the biggest impact on the score. And so because of that, they also would feel that it was effectively subjective. Now, it's not a subjective metric, right? It's objectively computed. It has it's a function that has 3 inputs, and if you put the same 3 inputs into it, it will always produce the same answer. But the fact that it was not well understood made it feel subjective. So if you said, and also the fact that we refer to it as complexity made it feel subjective, because developers might say, well, of course it does a bunch of stuff, but it's not complex, right? We would hear that all the time. What can we learn from this? One of the things that we learned is it's really important to use a metric or a set of metrics that resonate for your team. Metrics where if your developers are used to thinking about things in terms of cyclomatic complexity, then almost certainly cyclomatic complexity is going to be the best code metric for you to apply to start measuring the complexity of your code. Simpler metrics, counterintuitively, a simpler metric can actually be better than something that seems more sophisticated because it's easier to understand. So that's why now at this point we tell teams, if you can't decide what metric to use, just use lines of code. Because it's very clear if you tell somebody that you can set objectives and say, we'd like to keep our classes, let's say, smaller than 200 or 300 lines of code. A tool can easily validate that and provide you feedback when your class size is exceeding 200 lines of code. And it's actually very simple to know, what you could do about that if you wanted to. You could extract functionality from the class in question and create a new class or move that responsibility. Now, that doesn't necessarily mean that you actually want to do that. Ultimately, the decision about the way to organize the code is left to the experts and the software engineers on the team and shouldn't be driven by metric in isolation. But there's never a question of, well, how would I reduce the lines of code as this method? It's very direct. You get code out of there. So that's why if rather than spending a bunch of time trying to determine what the optimal metrics for assessing your code are, at this point we've learned to just stick with something as simple as possible, and then be able to get back to work and move on to bigger and more challenging problems. Okay, so the third question that I'd like to look at is, why are older projects harder to maintain? If you gave a developer a choice between a project which was just started last week and a project that was started 3 years ago, and that's the only information that they had, and you said, which of these projects do you want to work on for the next year of your life? I'm pretty sure 100 out of 100 developers are going to say, I would like to work on the project that just started, the code base that's brand new, because that's the green field, right? Everybody loves to work on a green field project. But and I think it's interesting to look at the reasons for that. And one of the reasons is that sloppy code is self-reinforcing. There are natural tendencies that make it so that once messy or sloppy code starts to be introduced into a code base, that is likely to perpetuate and compound. So we can just look at kind of how this might work. Generally, it starts with some sort of pressure. Maybe there is an external deadline. There's a big release milestone that needs to be hit. Usually this pressure is generated from outside of the engineering team for whatever reason. And the pressure leads to some measure of sloppiness because the developers feel like they need to meet other criteria that are not intrinsic to the code in order to relieve the pressure and hit maybe the time or scope-based release. The problem is that eventually the sloppy code can lead to the project being late because the developers feel like they're impeded by it and no longer able to deliver the code as quickly as they used to. And of course, the project being late or behind schedule leads to additional pressure. And then the whole cycle repeats itself. So this is something that we've seen at the core of a lot of the reasoning for why older projects tend to be harder to maintain than newer projects. Now, there's another reason that I believe this to be the case, which I think may be as interesting, and we call that technical drift. So if you look at this diagram, the line on the bottom represents a code base that's not changing, a code base that was written, and time is the x-axis here, and time is moving forward, but the code is not changing. Now what you see is over time, the domain drifts away from the code. And that's because if your code is written for a business, if that business is still operating, if they're still generating revenue, selling to customers, then even if you have a system that exists somewhere in that company, and that system is not being changed, everything around it is likely changing. The market is changing. The customers are changing. The focus areas of the individuals in that business are changing. And as a result, the domain that code lives in changes. And the delta between the domain as the code represents it and the domain as it would ideally be represented for the business can be sometimes referred to as technical debt. So the insight here is that code quality is actually a moving target. What could have been considered rightfully quality code at the time that it was written may cease to be quality code as time progresses and the ecosystem around that code changes, which is one of the reasons why older projects are harder to maintain. Now, there are a few different ways that people approach this problem. One of them is big design, right? So that would be representative of, say, going back, trying to remodel the application based on all of the learnings that have been generated over the past few years, and maybe rewriting the application or just making a big step function change to the way that it's organized and designed and the concepts in it. And that will sort of push the code much closer to the domain. Of course, then the cycle continues. The other approach is more iterative design. And that would be representative of trying to, in the week-to-week activities of the team, integrate realignment of the code that you're working on with the domain that it needs to represent as you're going. Now, the dark shaded area in the two charts, the big design example and the iterative design example, represents basically the tax on the team in terms of how much the technical debt might impede their ability to understand the system or to manipulate the system. And the nice thing about a more iterative approach is you see there's a lot less dark shaded area in the iterative design, meaning a lot less impediment in some cases for the developers. So sometimes this gets referred to as the Boy Scout rule. Does anyone know what the Boy Scout rule is, like in Boy Scouts?
No, it's leave the place better or cleaner than...
Yeah, leave the campsite in better condition than we found it. Be prepared is another great one from Boy Scouts to apply to code. But yeah, Boy Scouts try to leave the campsite in better condition than they found it. And you can apply this to your software development processes by trying to always leave the code base in better shape than it was when you check it in than when you checked it out. We'll go on to number 4. So what's the optimal size for a pull request? So I think this is a really interesting question, something that we've looked at a lot. So a company called Smart Bear Software did a study of about 2,500 code reviews at Cisco. And they were looking at a few different data points for each code review. One of those data points was how much code was being reviewed. What was the total number of lines of code in review? The other metric that they tracked, which you're seeing correlated here, is the occurrence of defects. Now, in this case, defect means a defect that was identified by a human reviewer. So almost certainly there are more defects than were identified, but this is what the human reviewers were able to find. And you can see that as the lines of code under review got smaller, the rate of the defect density, meaning the rate of finding a defect per line of code, actually went up. So maybe you've had this experience before where you open a pull request on one of your projects, and if you've got a 6,000 line pull request, you sort of open that PR and you ping your colleagues and you say, hey, can you review this for me? And what do you get back? And people are like, yeah, looks pretty good. But if you open a 50-line pull request, and you're like, what do you think? People are like, oh, that's wrong, and that shouldn't be there, and that name sucks, and they'll have an infinite amount of feedback. So this seems to be the case that fewer issues are found in larger pull requests. But our sort of intuition as developers is probably right that bigger pull requests are not less buggy than smaller pull requests. They're probably at least as buggy. So it's not because larger pull requests have fewer issues in them than the smaller pull requests. From the SmartBear study, they tried to sort of identify where that curve, what the right sort of point on that curve seemed to be as a guideline for the ideal size for a change. And the guideline that they came up with was to keep the pull requests under 400 lines of code. Beyond 400 lines of code under review in a single review, that's when the ability of a human reviewer to identify problems dropped dramatically. Or whether it's ability or fatigue, you wouldn't be as likely to get the value out of that review once it goes that much higher than 400. Now, being somebody who works a lot on static analysis, I think it's kind of interesting to think about code review from the standpoint of human reviewers, but also from the standpoint of automated code review or static analysis. These, we all have these robots now that can do things like run our tests for us and report the status of the test to GitHub. Your continuous integration system obviously doesn't care how many lines changed across a pull request, but it does affect the humans. So this reminded me of a quote from a guy, Brandon Keepers, who works at GitHub. He recently said, we're more receptive to feedback from pedantic robots than pedantic people, and robots are more reliable. So I thought about that a little bit when thinking about this lines of code change. An automated code review doesn't have that problem, but you're going to have the best results when you combine something like static analysis with a human. And if you want the human to be able to grasp it, you should keep them keep your pull requests smaller. So the next one, the next sort of question we're going to look at is, I think, one of the most interesting. When is sloppy code not a problem? When might it be superior to have sloppy, messy code than code that would be considered high quality? One case, I would argue, would be proving a hypothesis. In reality, the need to have high quality code is a luxury problem for a business, because it assumes that you're going to be around, that you're a going concern. Most businesses are not necessarily in that position, certainly not when they are created. So I think that if you're in a situation where it's unclear if what you're doing is actually going to be able to create any sort of positive business impact, and you'll be able to generate the business results that you are trying to achieve, then it may very well be more valuable to write something that is lower quality and may in fact end up being thrown away than to spend time worrying about the longevity of that code and how easy it is to be maintained in the future. And that can actually be incorporated into the process for scoping a project as a business decision. In fact, it's better to have those discussions explicitly between the engineering team who's going to be working on something and the business side who are sort of asking for functionality, rather than having that happen implicitly where not everyone's on the same page. There's a funny quote I like about this. As a bootstrapper myself, the quote is, there are two types of bootstrap startups in the world, those with integration tests and those with revenue. It's a little bit tongue-in-cheek, but CodeClimate is a bootstrap company. When I started working on it, we didn't know if anyone was actually going to use it or like what we did. But we started doing static analysis, and we actually score repositories on a 4-point scale between 0 and 4.0. The original CodeClimate codebase scored about a 3.1 on that scale. So we created a scale that we were ourselves not sort of keeping up with at the time. But it was very important. That second piece, the revenue piece, was very important because rent in New York City is unforgiving. So we had to fake it until we made it. And now the code is perfect. So I'm happy to report. Another one would be, perhaps maybe you know that a given piece of functionality is critical to the business, and the business is going to be around for a long time. But you don't necessarily know exactly how to model that code ideally, or you don't know what the right way to solve the technical problem in question is. In that case, it can be nice actually to build a component which is optimized not for being the most maintainable component over time, but is able to be discarded. So a lot has been written about the relative merits of big rewrites versus incremental refactoring. But that's usually supposing, in the context of an entire system, right? So are you going to rewrite your checkout system, or are you going to incrementally iterate it to be more maintainable? Which is an interesting question. But when you're talking about potentially writing a single class or a single module, I think that's where you can get a lot of bang for your buck by writing a class or module that is designed in a way where when you need to change it, when it needs to evolve later in the life cycle of the application, you can just discard the one that you wrote and rebuild a new one very quickly. So I don't think that this approach to software development gets spoken about enough, this idea of perhaps favoring disposable units of code over maintainable units of code. The last one, in terms of places where I think perhaps code that is more messy may be better than code which is clean, is this idea of a omega mess, which is a term coined by my friend Sandy Metz. And she defined omega mess to basically refer to messy code that has the quality of only really having inbound dependencies instead of outgoing dependencies, and that doesn't really change. Now, those things are very related, because if a piece of code depends on other units of code in your system, the more units it depends on, the more likely it is to change, right? Because unless those other units aren't changing, then it's going to need to change in the way that it talks to them. But you can think about certain areas of your code base where other code calls into the area in question, but it doesn't really call out to anything, or at least not to any code that you are responsible for maintaining. And in some cases, the logic that's encompassed in that area of code may not change for reasons that are sort of outside the scope of the implementation. An example might be Supposing you have a module which implements a SOAP interface for calling into a sort of legacy mainframe system, right? That old system is definitely not changing. There's literally nobody who's working on it at all. And that SOAP code doesn't call into any other areas of your program. It just receives calls and sort of bundles that up into a nice expressive and sort of callable component that the rest of your program can depend on. So it hides that mess, but it might be very messy internally. That would be a good example of an omega mess. And in these cases, I would probably recommend to teams that rather than trying to refactor that sort of library that integrates with that SOAP backend, it might be preferable just to leave it alone, especially if you're not changing it. Okay. So the last question I wanted to explore is what prevents us from having quality code bases? Because this gets talked about so much. I mean, developers love to complain about bad code. It's literally one of the core responsibilities of a software engineer. So, looking at potential reasons, is it apathy that we don't have good code? Is it because nobody really cares? I was really excited to find out that there's an emo Ontario. Maybe everyone's just fine with the idea. Who cares about the quality of the code? Is it ability? Is it the fact that we care, but the people who are working on the code actually don't know how to fix it? We're just kind of stuck with it because we can't really understand what we would need to do to make it better. I don't think that's usually the case either. Certainly in some teams, you have mixed experience levels, and not every individual will have the same familiarity with refactoring and principles for organizing code and testing and some of these disciplines that take years to develop. But that, I don't think, can explain the entire problem. Now, sometimes people talk about changing requirements. And this is in the form of, everything would be great if it just wasn't for those pesky business folks changing the requirements on us and, pulling the rug out from under us and, making the code do different things than they originally said. The changing requirements can certainly, as we talked about earlier with technical drift, make it more difficult and change the rate that the domain is evolving away from the code. And that can be a contributing factor, but I don't think it's the number one reason that it's very difficult to maintain quality code over the long term. So to answer the question, this is the diagram that I like to look at, and we'll go through it in just a second. But this is a diagram done by a guy named David Peterson, and he tried to illustrate how do developers with good intentions end up with crummy code bases. So we'll start here at the bottom. The assumption is developers do not want to introduce bugs. I'm pretty sure that none of us have ever sort of sat down at work one day and said, my goal today is to add more bugs to my code base. So that's pretty clear. But on the other side, in the back of your head, you might be thinking, well, it's pretty easy to introduce a bug when I'm changing code. That tends to be when they happen. That's when my thing breaks in production or on CI. So you take those two impulses together, and the developer might take care to minimize changes to the existing code. They don't want to end up creating bugs, of course. Now, if you're trying to minimize the changes to existing code, you might also realize that working on a copy of the code means you don't need to change the original, which is true. But the next logical step would be, of course, to duplicate the code. So you can leave the original and sort of not be at risk of breaking it, but you're going to need your own copy over here. So that creates duplication. Now, on the other side, if you're trying to minimize the changes to existing code, instead of duplicating the code, you might layer in more conditional logic, right? Because if you can sort of route around the path that you know works and just sort of handle your thing over here, then you know you're not going to break the thing that works. So you're going to get more conditional logic sprinkled into the code base. Now, these problems of conditional logic, overuse of conditional logic, and duplication, I think are kind of the yin and yang of unmaintainable code. Of course, conditional logic increases complexity and perceived complexity and decreases developers' ability to understand, right? So because the code base is becoming more complex, the developers are having trouble understanding the ramifications of any changes they might make in the future. And this comes right back down to where we started, which is an increased feeling that it's easy to introduce a bug when changing code. So I find this diagram fascinating. At every step in the diagram, the developer might be making a perfectly rational decision with good intentions, but nonetheless, they wind their way through this flowchart and end up perpetuating this cycle where duplication and conditional logic gets introduced and they can't understand what's happening, and that just goes on and on and on. So what's driving all of this? Why don't the developers just fix the problem that they're faced with instead of trying to tiptoe around it? And this is the answer. It's fear. Fear is the #1 enemy of quality code, in my opinion. The more the developers fear making changes to the code base or confronting the problems that are inherent to the code, the more they will do backflips and tiptoe around and dive out of the way of problems, which create second-order and third-order problems that just perpetuate the cycle. So if you want to improve code quality within your organization, what you really need to be, and you're finding that the reason that people aren't improving the code is not because they don't know how, and it's not because they don't care, it's because they're afraid of breaking anything. Then you really need to target that and focus on how can we reduce the fear of our developers when they're making a change in their day-to-day and week-to-week work. So there are a bunch of strategies for doing this. We definitely don't have enough time to dig into them all today, but you're going to want to reach into your toolbox and look at things like automated testing. Do our tests fail when we break something, and do they pass when we don't? The more that that's not true, the more scared a developer is going to be that they broke something. Operational metrics. So your unit tests are never going to be perfect, but how quickly can you detect in production that you broke authentication? Well, if you can know that in, let's say, a minute or two, for most applications, it's not really that big a deal if the system wouldn't let anybody authenticate for a couple minutes, and you figured that out and you rolled it back. But you're going to need to have the visibility into your operations to be able to do that. Code review, which we've talked about a bit, from other people on the team looking at it. At least then, if something goes wrong, it was, you have 2 people who had to get past before it made its way to production. Static analysis, near and dear to my heart, can help reduce certain types of bugs. Pair programming, which is somewhat controversial, but is an extension of code review to make it continuous. All of these are techniques that you can deploy in your organization to try to reduce the fear of these developers in in making these changes. And if you can continually chip away at that atmosphere of fear, I think you're going to see better results when it comes to reducing duplication, reducing complexity, and taking that vicious cycle that we saw in the diagram and sort of flipping that on its head and having things perpetually get better. So overall, if you find yourself with a code quality problem, and many of us have had them, sometimes they feel intractable. It feels like we know something's wrong, but we don't know what we're going to do about it, and that can be very demotivating. There are things that you can do about it. There are practices that you can employ. They're not going to be silver bullets or overnight fixes. But if I can leave you with anything, I would say hope is not a plan. It's not going to get better with just hope. And you have to actually decide what you're going to do as a team, get everyone on the same page, commit to doing it, and that's your best chance of success. So that's what I've got. Thank you very much. And we've got some time for questions. I think we're going to be running a mic, so if you have a question, please just raise your hand way up high and they'll run the mic over to you.
Probably a stupid question, but what's static analysis?
Yes.
What is that?
Static analysis is basically using algorithms to derive information from code. So that could be as simple as a metric, like the ABC metric or the cyclomatic complexity metric, computing something like that. Or it could be more sophisticated, like doing a data flow analysis to determine that you are taking unsanitized user input and handing it to the database in some way. All those would be forms of static analysis. CodeClimate does static analysis on every when you open a pull request, and then we feed that into the developer's sort of code review workflow, but there are many ways to do it. Yeah.
So first of all, thank you for the talk. It's very informative. As far as your number 5, the sloppy code and proving a hypothesis or building the first one and throwing it away,
yep.
How do you prevent that code from the second that it gets out the door, a customer says, great, put it in production now, and oh, by the way, add these 3 features?
Yeah. So in a word, trust. And that is a trust in communication, really. And the healthier your internal communication and your internal trust is between the technical people who know that if it gets shipped to production, that they're going to be stuck maintaining it forever, and the people who are sort of on the business side trying to drive requirements and test hypotheses. The better that you're communicating and trusting each other, the more it's a competitive advantage because it gives you more flexibility to use these, this type of approach and iterate faster. Now, if there's a history in the organization of the engineers building something, saying, oh, it's just a prototype, and then if we want to productionize this, we're going to need this, this, and the other, and people on the business side saying, oh yeah, of course, and then that not actually happening, what you'll likely see is the developers being less interested in sort of trying that type of experimentation going forward, and then it just removes that tool from your toolbox. So. It was nice when CodeClimate was just starting. It was just me programming, so I was both the engineering guy and the business guy. And so when I deployed something that was a prototype to production and it broke, and then I was stuck maintaining it forever, I really just got to yell at myself. But that's the crux of it, I think. Other questions? There's one over here.
For CodeClimate itself, the results that you get from analyzing code, do you feed that back in to learn and make your analysis better? And if you do that, how do you convince people to throw their proprietary code into it?
So primarily, the types of checks that CodeClimate performs are basically patterns that are common defects and that are sort of applicable to a wide array of projects. We run a set of checks against each project, and that produces basically our database, which is all these defects. We're not doing anything right now where we're taking the occurrence or prevalence of these issues and things like false positive rates and using that to, on a systematic basis, improve the algorithms. But it's something that we would like to do.
And do people surrender their code to you in terms of the proprietary nature of it? And
yeah, so the way our tool works is we connect to your source code wherever it is in GitHub or Bitbucket or something like that. So yeah, the 1,500 organizations from the slide in the beginning, those are organizations that are getting our help with finding issues in their private source code. And so, we silo that, and just like GitHub, it's sort of limited specifically to them. But there's definitely the opportunity, I think, to, done in the right way with things like opt-in, let people sort of help make the system itself better.
So at the beginning of your talk, you were talking about as a team, we should be agreeing on what complexity we're using, whatever.
Yeah.
So I work at a large company, and we sort of get these corporate mandates. What is your opinion of, what size team? Because I do know if I'm working with another team, it is nice to be on the same page, but at the same time, it'd be nice to have our own decisions. What's your opinion of those kinds of decisions?
Well, so my perspective is probably a little bit biased because over the course of my career, I haven't worked on any engineering teams that are very large. I think the largest engineering team I worked on was maybe a little bit short of 100 developers when I was there. And obviously there are engineering organizations with hundreds of developers, thousands of developers, and I've just never worked in one, so this isn't necessarily my specialty. But from what we've seen in trying to help teams within those large organizations with their code quality is, by and large, there is focusing on the context for the team is much more important than the sort of overall organization in order to be successful. So when we're deploying, let's say, Code Climate into an org with 1,000 people, we'll start with usually 30, 50 people, something like that, who tend to be working on the same projects and be at least somewhat like-minded about what they're trying to achieve, and get that working before expanding into other teams. And then with each team, we basically go through the whole process again from step one, which is, okay, what are your pain points, right? Is there really, to get to the goals, one of the first questions we'll ask is, well, what's going well, what's not going well, right? And that's where you can usually generate, that helps generate consensus. But because one team might tell you, well, we've been noticing that a lot of code is duplicated, and we've been having a lot of bugs in production, and then you can sort of build on that to potential solutions. But if a team over here is not experiencing the same problems, and you come to them with the same solutions, they're going to look at you like you're crazy. Well, why are you trying to solve this thing? We don't have that issue. So we try to go back to square one on a team-by-team basis. Now. Certain organizations definitely do try to do more top-down management of this sort of thing, and I think even if the individual team goals are different and they evolve, and they're especially going to evolve over the life cycle of the project, right? A project on day one doesn't have the same needs as a project that's been around for 10 years, but you can start to look at some higher-level metrics across all those projects to see how they might be relating, but that's really a different use case than okay, I have a problem, I'm trying to solve it and improve the code on a day-to-day basis. Hopefully that's helpful. Great. There's a couple of questions over here.
Thanks. Do you find that once a client submits a project and gets an analysis done, if they submit any subsequent projects, that they tend to have better quality code than they did initially?
Yeah, so it's an interesting question. We definitely see teams that adopt Code Climate, and then they, so generally when a team adopts Code Climate, they will, choose a set of static analysis tools to apply, static analysis rules to apply, based on their goals, right? So start with the goals, then you end up with the configuration, and that results in a grade. That's the 0 to 4.0 grades. Very few projects that are meaningful in terms of their business impact will tend to score highly on, very highly on that scale on day one. If a project is, loaded into Code Climate and it scores perfectly on the different ratings, we have an out-of-the-box configuration, almost certainly there's very little code there, which I think is interesting and relates to the question of, well, can you use lines of code as a solid metric? But over time, the teams that integrate it into their pull request workflows will improve their ratings, and then when they start new projects, going forward, generally we're brought in on day one, which makes it a lot easier, because if you don't, if you can avoid sort of digging a hole, or at least to some of the stuff we were talking about earlier, digging a hole without realizing it, then you're in the best possible position to keep your code at the standard that you want at all points during the project. Question over there.
I was curious if the tool allows for, and if most teams do, track kind of multiple metrics that might show if a team is like optimizing around the score rather than around actual good code. So like the simplest example would be lines of code, just golfing your code down, making it less readable to get the 4 score when you put up the pull request. So
just more semicolons and just keep removing new lines.
Right.
Gamification of static analysis metrics is, I think, a really fascinating sort of question and concept. Because there is definitely a risk of somebody taking an action simply because the tool sort of told them to do something or told them that something might be problematic. The best solution that we've seen for that is combining the automated feedback mechanisms with human review cycles. So if you're responding to feedback from the tool, ideally, we like to suggest that, let's say Code Climate tells you that your class is too big. And it's too big because it has too many lines of code. You've said you want to keep your classes generally under a couple hundred lines of code, and yours is now, 203, right? So that's a really interesting case to me, because the first thing that developers say, it's always the same thing. They go, well, it's just a little bit over. I only needed to add 5 lines. It was 198 lines before. Now it's 203. These 5 lines look pretty important. But the problem with that line of thinking is, no class ever became 1,000 lines of code by jumping from 10 to 1,000. It started at some point along the way, if you were to draw out the history, it slowly got bigger, right? So what we like to suggest is that when Code Climate flags something and says, okay, your class is a bit bigger than the threshold that you've identified, is that becomes the starting point for a conversation within the team. So maybe the person who made that change or the person who's reviewing that change uses that as a prompt, not to say, oh my gosh, this is 3 lines over, where can we remove some white space? But to say things like, well, have we considered other ways for organizing this code, and what was our sort of assessment of those alternatives? Or how do we see this code evolving over time? Do we see that this is its core responsibility set, and really there's nothing else that we expect to be introduced here, or that this is going to continue? We see these case statements and they continue to grow, and sure, we just added 5 lines, but we can see in 6 months it's going to be much bigger. So through those conversations, I think is the best strategy to inoculate against gamification. When the gamification happens, it's generally one developer acting in isolation. So I think that those are the 2 ways to balance it. One in the back.
So with all the code bases that you analyze at Code Climate, have you noticed anything interesting in aggregate across languages or platforms or anything like that?
We have not nearly done enough mining of our internal data. We definitely need to load up a Redshift database at some point soon. The one thing I would say, this is more qualitative than quantitative, is that it was remarkable to me that the types of conversations that we have with developers about code quality and their goals and the strategies that they're employing are remarkably consistent across different languages. So we started with Ruby, and then we added support for PHP, Python, JavaScript, and now we have about the better part of a dozen languages that we support. But the archetypes are all the same. The implementation details obviously differ, but the problems aren't new. And I thought that was pretty interesting, the consistency of sort of how that maps out across the different language groups. C is not yet included in that list, but will be. Yes.
I agree that fear is the number one cause of why we don't clean up our code. I also think that on the other side of that, we know what to do. We know how to clean up the code, but then that takes up more time, which alludes to what you was talking about in the beginning of your slides.
Well, so it's a question of, the question of, okay, well, I'd like to do more to improve the quality of my code, but it takes longer, I think is in part a question of perspective, right? So if you separate the activity of improving code from the activity of writing code, then it's naturally going to feel like to do the writing and the improving takes more time than to do just the writing. But in my head, I try to avoid drawing that distinction and instead think of that entire activity as just writing code. And then there are there are different contexts when I'm writing code where the correct way to write it or the optimal way to sort of write it may vary based on things like the business factors that we spoke about earlier. But it's all the same core activity of the software engineering itself is one way to think about it. I can do two more. There's one here, and then we'll do one in the front, and then I'll let you all get to the bar.
In terms of dealing with lines of code in a class or object going over some sort of threshold, is there some sort of metric to keep people from writing really small methods in code with lots of layers of abstraction that are hard to mentally deal with? How does that kind of dilemma managed?
Sure, you could have a metric which is the number of methods. That would be the simplest way to do it. So we have a check, for example, for Ruby code where you can say, okay, I want my methods to be no larger than this line of code length, but I also want to make sure that if a given class ends up having upwards of 20, 30 methods or something like that, then I'd also like that to be more visible and prompt a conversation. So the example of it can be useful to take metrics and pair them together, where you have one metric that's creating pressure on one side and then another metric that's creating pressure on the other side. And then you're trying to find some kind of balance between those things, or at least make it explicit that there's a trade-off and that there's probably a fairway in the middle that you're trying to run down. So that would be a good example between sort of refactoring, overfactoring. Duplication versus complexity in some cases have natural tension between copying code and also reducing complexity. So I think there are ways to do that at the small level with different combining multiple metrics together. Do one here, and that'll be the last one. But I'll be around, so we can chat after.
Thanks. So you talked about some of these interesting, essentially stateless metrics, like Cyclomatic and lines of code.
Right.
I'm curious if you've looked at or contemplated kind of historical trend lines, right? For example, does change density within a function or method indicate bandages piled on top of bandages, or somebody sanding and polishing to a fine degree?
Yeah, no, it's a really good question. So we haven't done much with that. We've done some basic analysis of top-level project history, basically Git history, and looking at things like how did the number of authors correlate with higher or lower scores. But at the per unit of code level, I think it's pretty interesting to incorporate the history dimension. It's like the extra axis. There's a project that I saw, there's been a couple projects which actually try to identify how buggy a given piece of code is from the history. And the way they do that is by looking for commit messages which have the word bug or fix in them, and then looking at what they change. And so it's just a simple, imperfect correlation that, well, if this class continuously gets changed in commits that have the word fix bug in the message, it seems to have a lot of bugs, or it did, and it probably has more. So I think there's a lot that can be done there. We've just started scratching the surface. I think we'll call it there. Thank you everybody so much for your time and attention. I'll be around. You can chat more.